Hello everyone. So in this video we're going to talk about section 8.2 inverse trigonometric functions continued. So in section 8.1 in the last two videos we talked about inverse sine, inverse cosine, and inverse tangent. In this video we're going to practice a little bit more with those, and then we're going to learn about inverse secant, inverse cosecant, and inverse cotangent. And as you might imagine, they're going to follow along similarly with what we did before. So let's first look at an example of putting together an inverse function, but not with the regular function counterpart. So in the last couple videos, we talked about sine and sine inverse and how they work together, but we didn't talk about how inverse functions of other ones work together. So here's an example. I want to find the exact value of the expression, the sine of the inverse tangent of 1/2. And so now we can't rely on what we would hope as that nice rule that said the regular function and the inverse function would cancel out. Well, clearly sine and inverse tangent are going to cancel out. So we need to think of something else. And so we're going to use the general strategy that I've been using the whole time, and that is we're going to set the inverse part, or the inverse function, to be theta. So this is different than what we've done before. Usually we've set the whole expression equal to theta, and that was always the case because the inverse function was on the outside. But really, I'm using that theta equals stuff to just get rid of the inverse tangent, or the inverse whatever, the inverse function, because I don't know how to work with them very well. So I need to get rid of them in some way. And so here I set that in the inside inverse function equal to theta. Okay, and so then I have theta equals the inverse tangent of 1/2. And from the last video, we know kind of how to work with that. So we take the tangent of both sides, and what comes out after some algebra is that the tangent of theta is equal to 1/2. Okay, and I know that theta lies between -pi/2 and pi/2, not inclusive. And that's by the definition of inverse tangent. So now I have some information about theta. Okay, I don't really know what theta is, and it doesn't fit any of the 30, 60, 90 or 45, 45, 90 triangles that we know that have the two sides equal to 1 and to 2. We have the side and the hypotenuse equal to 1 and 2, but not both sides. So because this is tangent, it's not quite what we're used to working with. So I have a picture down in the bottom right that we can glean some information from. So being that I know that tangent of theta is 1/2, I could then further inform or further investigate and find that tangent is only positive in the first and the third quadrants, and I know theta lies in the first or the fourth, so it has to be in the first. And so I drew my triangle in the first quadrant, you'll see in the bottom right, okay? And I know that the opposite side of the angle is 1, and then the adjacent side, when compared to the angle, is 2. And so when I use the Pythagorean theorem, I get that the hypotenuse is the square root of 5. Okay, so that's great. Now we have some information about the triangle. We don't really know what the angle is, but it turns out that the angle theta is not really important. So when we set theta equal to inverse tangent up there, in the first step, what we really simplified the actual expression that we were looking at to was sine of theta. Okay, when we set theta equal to inverse tangent, that's what we have now, is the sine of theta. And so with the triangle that we have in the bottom right, we can actually find what the sine of theta is. And it's opposite over hypotenuse, or 1 over the square root of 5, which would then, when you get rid of the square root in the denominator, would give you square root of 5 over 5. Okay, and so that's an example of working with two functions and inverse functions that aren't the same. Okay, so here's another one. Now cosine and sine. Same sort of thing. Okay, same sort of thing. I set the inside equal to theta. I have the sine inverse of negative a third is equal to theta. I do my algebraic steps that I've been doing the whole time, and I get that the sine of theta is equal to negative a third. Now I have to think, where is, I know that theta, because of inverse sine, is defined in the first and in the fourth quadrant, okay, between negative pi over 2 and pi over 2, in the first and fourth. And where is sine negative? Well, everything's positive in the first, so it must be that theta lies in the fourth quadrant. So that's why I've drawn the triangle over on the right in the fourth quadrant, because of that information. And so I have that the sine of theta is equal to negative a third, and so that the opposite side must be a negative 1, because hypotenuse is never negative, and the hypotenuse is 3. So that leaves the adjacent side to the angle, unknown, and I can solve for that using the Pythagorean theorem, and I get 2 root 2. Okay, and so with that information, I can then find the cosine of that angle theta. So the only difference between the last problem and this problem is the last problem I gave you a nice visualization. Here I had to make it myself. But the same exact thing, cosine of theta is equal to the adjacent over the hypotenuse of the triangle there, and so I get 2 square root of 2 over 3. So hopefully that made sense. These are 2 examples of other stuff that we didn't really see in section 8.1, but is still important. Okay, so let's move on to the inverse, cotangent, secant, and cosecant functions. All right, so I'm going to give you a visual picture just as a refresher of what the 3 functions look like, and then you can visualize what the inverse function is going to do. So cotangent looks like this, okay? Very similar to tangent, but it's flipped around the x-axis, and it's shifted over by pi over 2, okay? But so you can imagine that inverse cotangent is going to work similarly to inverse tangent, and then here's cosecant and secant, and so you can go back and you can kind of think maybe what they're going to look like as the inverses. Okay? All right, so first example of using an inverse cotangent, inverse function that's either cotangent, secant, or cosecant. And before we start, the general idea of what we're going to do is we're going to try to avoid these 3 functions that are lesser known than sine, cosine, and tangent. If we see the sort of non-standard 3 trig functions, we're going to try to convert it to one of the 3 standard trig functions. So for inverse cosecant of 2, what we're going to do is what we always do, set it equal to theta, okay, and then get rid of the inverse. Cosecant of theta is equal to 2. Great. What's even better is that cosecant is the reciprocal of sine, and so sine of the angle theta is equal to 1 over whatever cosecant was, which is 2, and so sine of theta is equal to 1/2. Okay, great. So sine of theta is equal to 1/2. I know that theta is between negative pi over 2 and pi over 2 from the information that we found before about inverse cosecant. Okay, it's going to work very similar to inverse sine. So inverse cosecant, the theta is defined at the same place. Its range is the same as inverse sine. It's defined in the fourth and in the first quadrant. Okay, sine is positive in the first, and so I have 1/2, which turns out that that's our special 30, 60, 90 triangle when the opposite side is 1 and the hypotenuse is 2. That means the other side is going to be root 3. And then the angle that's opposite of the side that has length 1 is 30 degrees, or pi over 6. And so then that's the answer. The inverse cosecant of 2 is pi over 6. Okay? So hopefully that made some sense. Now, using the calculator to evaluate these inverse trig functions is maybe slightly more complicated than it was for the regular three inverses, sine, cosine, and tangent, because there are no inverse cosecant or inverse secant or inverse cotangent functions on your calculator. So if you can look as much as you want, they're not there unless you have a really fancy calculator. So what you need to do is again manipulate what you have into another form that involves tools that you can use. Okay, so for instance, the first one, inverse secant of 3, I want you to find the approximate value. Okay, and so it says exact, it should say approximate for each of these. These are typos, that's my bad. And so when I do inverse secant of 3, you're not going to find an inverse secant of function on the calculator, so you need to change it. So we do our same exact thing that we always do, set it equal to theta, okay? And then, so we get that the secant of theta is equal to 3, great, okay? And because cosine is the reciprocal of secant, the cosine of theta is equal to 1 over whatever secant was, which is 3. So cosine of theta is equal to 1/3. And then I can move that cosine back over with the inverse operation. And I get that theta is equal to the inverse cosine of 1/3. And so I do have that function on my calculator. Okay, so you can do cosine inverse of 1/3. Remember that your calculator should be in radians, and when you do that, you should get 1.23 around that number. Okay, and so that goes the exact same for each one. Okay, and you're always going to use those reciprocals, those not co-functions, but the reciprocal functions. So sine and cosecant, cosine and secant, and cotangent and tangent. Okay, so hopefully that makes sense. If it doesn't, please feel free to contact me, email, Zoom, whatever, and I can explain again there. All right, and so the last thing that we're going to do, and this is probably the toughest out of any of the two sections, is we're going to write an expression that involves an inverse function as an algebraic expression containing one term u. Okay, and so you could use x here if you want to, but we use u. And so I want to get rid of all sines and cosines and tangents or inverse functions at all. I just want an expression that only has u in it. Okay? Only has u in it. So what I'm going to do, same thing that we do every time, set the inverse part of whatever the expression is equal to theta. So I set theta equal to tangent inverse of u, and then when I take the tangent of both sides, I get that the tangent of theta equals u. Okay, so that's the first part. I know that u is equal to the tangent of theta. So what I want to do is my original equation is now simplified to just the sine of theta. Okay, so I have that the sine, the expression is equal to the sine of theta, which is okay, but that's not in terms of u. So what I need to do is to get sine of theta, or whatever expression that I come up with, to only include tangent of theta in it. Okay, it can include multiple tangent of thetas. They could be all over the place, but that's the only thing that should be there. So I start with sine, which is not great. There's no easy or real easy way to get to tangent, but the one thing that I do know that a fundamental identity is that tangent is equal to sine over cosine. And so if I can multiply by 1 in a clever way, then I could get tangent. And so that's what I do. I multiply by cosine of theta over the cosine of theta, which is 1. And so I'm multiplying by 1, not really doing anything to the expression, but that gets me a sine over cosine. And so sine over cosine is equal to tangent. So that leads me to the third step, and now I have tangent of theta times cosine of theta, which is good, that's better, but I need to turn cosine into just tangent, okay, in some way. So you have to think about what other identities I know, what's connection with tangent. And so the one that will hopefully come to mind is the fundamental identity that says 1 plus tangent squared is equal to secant squared. Okay, and I wrote that down here, so that's surely clear to all of you because it's written down here. But now I have a way, and I know that cosine is related to secant because they're reciprocals. And so if I can do some manipulation there, maybe I can get all tangents. And so that's what I'm going to try to do. Cosine is equal to 1 over secant. And so then I can change that equation into tangent over secant. Great. And then I know that secant squared is 1 plus tangent squared. So secant is equal to the square root of 1 plus tangent squared. And so that gets me to the final part of the expression, which is tangent of theta over the square root of 1 plus tangent of theta. And then I know that u is equal to the tangent of theta, and so I just substitute u's in, and I get u is equal to the whole expression is equal to u over the square root of 1 plus u squared. Okay, so that was, I'm sure, very simple for all of you. Hopefully you were able to follow along at least with what I was trying to do here. I'll be honest and say that this is not going to be a large part of the final exam and your homeworks and your quiz for this week, but it is there slightly, and so you have to know sort of what's going on. Okay, but that is definitely one of the harder things that you'll see of how we do, of what we do in this section. Okay, so thank you. That's the end of this video and the end of section 8.2.